Hello, everybody. Hello, Java developers. Hello, all the developers. Once again, here we have an amazing session. This is Muad bin Ali. I'm the principal engineer and I'm one of the organizers of the Riyadh Java user group. So we had a couple of amazing sessions in the past. So here in Riyadh Java User Group, we organize sessions, talks, open discussions for all Java-related topics. So we welcome everybody to join our meetup group and to subscribe to our YouTube channel. And regarding today's session, let's welcome our guest, amazing guest, Tiz Van. Hi.
Hey there.
Hi, how's it going? Thanks for joining us.
Doing well. Happy to be here.
Yeah, thank
It's
you
a
so much.
subject we like to talk about. So,
Yeah. So we are very excited for this subject, and let's give a brief introduction about our speaker today. Uh, Tiz Van, he is an amazing software engineer. He is like one of the guys who loves to share the knowledge and to speak in public sessions, public conferences, and he's very passionate and also a coach. So please find him in Twitter at tease underscore Vin. So please follow his Twitter account. And if you have any questions regarding today's session, please drop them in the comments below. Before we give the stage to Taze, so I would like really to all of you encourage and please interact with the session. So stage is yours, Taze. Good luck, and we hope to enjoy this session. Thank you.
thank you. Yeah, indeed. Just post whenever you have a question. It also makes it more fun for me. So, welcome to my talk about empowering your development with functional programming. So, a bit about myself. My name is Ties van der Ven, a very Dutch name. I'm from the Netherlands, as you can maybe also tell by my accent. Currently, I work for a company called Alliander, which is a Dutch power grid operator. And you may think, what does power grid have to do with IT? Well, in practice, we hire about 1,200 developers and 200 teams. And my job there is software quality expert. And as a software quality expert, I try to help all those 200 teams improve the quality of their software. And I get to call myself expert, which is pretty cool. So my background is in Java, mostly Java. Also did a bit of Kotlin and even did a bit of Scala. And I'm a bit of a functional programming advocate, although that's not really true. That's more of the easy way to put it. I'm more a fan of software engineering fundamentals. So programming is basically just applied mathematics. So if you ask the question why enough times, you end up with category theory. Well, I don't know category theory. So one step back is basically functional programming. And that's a lot easier to understand. So mostly advocating for why you do certain things instead of the how. So that's what we're going to talk about today. We're going to talk a bit about what functional programming is, and the four main topics today are composition, state management, error management, and side effect management. See, out of these four main topics, I would say composition is the one that's mostly related to functional programming, although it's used in other paradigms as well. But the other three are mostly mentioned in the context of functional programming, which is a bit of a waste, in my opinion, since these problems happen in any language, in any paradigm. For me, these are fundamentals. So in a way, this is not really a functional programming talk. This is more software engineering fundamentals talk. So these are the basic concepts that you can use to reason about more complex stuff. And we'll see a little bit of that as well. So why functional programming? Well, one thing functional programming is known for is reusability, as in they say object-oriented programming is reusable, but because you have reusable components, but in functional programming, we have reusable functions. which are basically small components. And they're reusable to certain extremes, up to the point that it's basically impossible to read the function signature anymore. But they're very reusable. Another big part of function programming is its terminology. This is what scares off a lot of people when you start talking about monads, monoids, functors, semigroups, all that kind of stuff. Well, we're not going to use any of those terms in this talk. We are going to talk about all of those. We are just not going to use the terminology. So you'll hopefully find out that most of the things of all those words you actually use on a day-to-day basis already. And it's mostly about the way of thinking. You can do functional programming for years without knowing the terminology or even knowing the mathematics behind it. You also don't need to know that stuff. Although it does help a bit to know the terminology. It did help me in my way of thinking because instead of having some vague concept, that now you suddenly have a word for that concept, which means your brain has a little bit of a short circuit or a shortcut, sorry. Maybe also short circuit, talking about function programming, but in a way a bit of a shortcut. So it makes it a bit easier to think about certain concepts and therefore easier to reason about certain things. And if the other person also knows the terminology, it's easier to communicate. And the big thing from function programming is complexity management. So this is what we're trying to achieve. We're trying to create less complex applications. And here also lies a bit of the problem with functional programming, because not all applications are equally complex. Some applications are very, very simple, as in near trivial applications, like, for example, something that reads a file from the file system and just outputs the results in console. That's near trivial. And on the other hand, you have extremely complex systems, like, for example, what Amazon tries to do. And your application will probably be somewhere in the middle. So the irony within functional programming is that if you try to apply complexity reducing things to something that's already very simple, what happens is, ironically, you make it more complex because there's no reasonable way to actually make it simpler. So some principles that we're going to talk about today won't really work well here. But on the other hand, things you can get away with on this side, you really can't get away with doing on this side, because then the complexity comes out of control, and then you have basically the whole spaghetti go tired up monolith sort of things. This is also, by the way, the problem why it's so difficult to explain functional programming, because you want to explain things using very simple examples that people don't have to think about. But yeah, adding functional programming to that bit can make it seem more complex. So that's the irony of functional programming, and makes it difficult to teach. So let's talk about our first main subject, composition. So composition, everything is about functions. And function signatures are a very good way to reason about functions. It's just taking a step back and looking at functions in an abstract way. So a function signature consists of the input and output of a function. So we don't care about the name or the body, only the input and output. So the top function turns a person into a string. The second function turns a string into an integer. And if we combine these two functions, then we suddenly get a function that turns a person into an integer. And this is the basis of function composition. It's basically chaining functions together. A good way to symbolize this is using dominoes, as in the original game, not the one where everything falls apart in the end. But every stone can be considered a function, which has a certain number as inputs and a certain number as output. And as long as the output of one function matches the input of another function, you can combine these. And if you do this long enough, you can create a whole chain of functions and create actually quite complex software indeed. And your brain already does this. If we would take a simple software engineering problem, like given a list of persons, sum the total age of everyone with a name starting with A. There are quite a few ways to solve this problem. So if you think a bit about your head, like how would you solve this? There are no wrong answers to this. One way to solve this is, for example, a for loop, where we have a variable total length, we loop over the persons. If the person starts with an A, we get the age and we apply it to the total length. And this is a perfectly fine solution. There's nothing wrong with it. But it is good to appreciate what your brain did here when it came up with this answer. Because if you look at our problem, it actually consists of 3 separate problems. Namely, only select the people with names starting with A, get the ages of all the people, and sum all the ages. And if you came to the for loop, that means that your brain managed to figure out that problem actually exists, has 3 separate subproblems, and solve them all at once in one block, which is quite impressive. So well done to your brain. But this also shows the benefit of tearing a problem down into subproblems. And this is why I love the streaming API in Java. Because if you look at that implementation, we can see that first we stream a group of the persons, we filter out all the persons starting with an A, we get all the transform them to all the ages, and then we sum them. So the streaming API is, in my opinion, so good because it really embodies this way of destructuralizing problems into separate, smaller problems. And this scales way better. The more complex our problem becomes, the more complex our for loop becomes. But for every subproblem, only one line gets added here. And that's a very powerful way of thinking and for complexity scaling. What also helps is that all problems now have its own separate name. If you want to remove elements from the stream, it's called a filter. If you want to transform something, it's called a map. And our sum is, in our case, actually called sum. So we're also starting to think in standardized problems if we do it this way. So composition is a very powerful way to solve problems. Another good example of that is Linux. Any Linux users here? No one dares to type, no problem. Personally, I still use Windows, although I can't really work without installing Linux subsystem anymore because Linux has a really cool feature. Like my favorite feature of Linux is this symbol here in the middle, the pipeline symbol. So what this does is it takes the output of ls and feeds it into grep. And it can do this because the output of all programs within bash is a byte stream and the input of all programs in bash is a byte stream. Therefore, the inputs and outputs of all programs match, which means you can compose them together. So the whole power, in my opinion, of the bash shell is just pipelining, which means function composition. And even myself use it to create very powerful bits of software on the spot to solve my specific problem. So function composition is really powerful. And turns out we can also use this for problem solving because this is what most of what we do as software engineers. We solve problems. Like the actual coding bit, that's maybe like 20, 30%. The rest of the time, our brains are busy trying to figure out how to solve the problem. And the nice thing, as we just learned, problems can be divided. And I wanted to share a bit of a trick that I use to solve complex problems. And the first thing we have to do for that is take a big step back and look at the problem in an extremely abstract way. So if we have to build a microservice and look at it from a very, very far perspective, what we get is this. We have some JSON, we feed it into a program, and out comes some JSON. And this basically describes nearly every microservice ever. But we can now start dividing up the problem into separate problems. So our program probably first needs to parse a JSON, which creates some parsed input. Given some parsed input, we feed it into the logic and out comes some JSON. And we can probably split up the logic bit again. So first we have some parsed input, then we'll enrich it. Then we have some enriched input, which goes into logic, which goes into JSON. And we can probably split this up many more times. But if we do this enough times, in the end, we reach a point where it's very, very difficult to split up problems even more. And now you have a whole tree of all the subproblems that need to be solved for your main problem to be solved. And if you chain all those small functions in the end together, then in the end, you solve the problem. And what I really like about this method is right now, we're only thinking in the different steps we need to solve a problem. We only think in state changes. Given JSON, we go to parsed input. Given parsed input, we go to enriched input, etc., etc. So we're not even thinking about which frameworks we're using. We're not even thinking about which paradigms we're using or which programming language we're using even. We're just focusing on all the steps that are needed to solve the problem. And no matter which language, frameworks, or even how many microservices and such this would contain, these are all the steps that are needed to solve our problem. Which means it can apply to pretty much any situation. And I use this all the time if I need to solve complex stuff. So hopefully it's helpful for you as well. So the key takeaways here are that most problems are actually compositions of subproblems. And the streaming API is a very good way to first represent this, but also train yourself to think in terms of breaking up problems, and especially if you can assign a standard name like map or filter to them. So if you haven't been using streaming API until now, yeah, that's a good idea to start doing that. Which brings us to state management. So state is the most difficult problem within software engineering. Almost any bug I ever solved is in one way or another related to state. So state is basically all the values within your application. And state can actually make things quite complex. And to give a bit of an example of that, let's assume I have a car, like a red car, and I want to turn it into a blue car. So let's take a look at how object-oriented programming would solve this problem. So object-oriented programming kind of likes to model itself to the real world. So in the real world, I would probably take my car to a garage, get them painted, and then out comes my newly painted car. So object-oriented programming kind of likes to do this. It creates a car, it has a private string of color, a getter, and of course a setter. So we take our red car and we call the setColor method and making it a blue car. And now my red car is blue. So how would a functional programming do this? A functional programmer would do it slightly different. A functional programmer would take a very good look at the red car, start building an identical car right next to it, except until the painting needs to be done. It then paints it blue instead of red, and then it destroys the red car. And now the functional programmer has a blue car. And financially, that might not be the best decision in real life, but it actually does have an advantage. Because if you go back to our object-oriented programming car, if I ask you the question, what color are you? What are you going to get back? The answer is, it depends. Do you ask that question before the car is painted, or you ask the question after the car is painted? Suddenly, it matters when you ask the question to know what answer you're going to get. Well, if you ask either of the functional programming cars, what color are you? You will always get back the same answer. And this is what makes mutable state, by definition, always more complex than immutable state. Because mutable state adds a complexity of time. Now it fully depends when you ask a question. And immutable state doesn't have this problem. So mutable state is by definition more complex than immutable state. And so many problems are being caused by mutable state. Things like race conditions and all kinds of concurrency problems and such. And this is also where a lot of functional programmers will start talking about how immutable state helps with concurrency. But in practice, most engineers I know don't really work on highly concurrent applications on a day-to-day basis. So I figured that's not a really good angle to talk about this problem. So instead, I'll focus on what it does to the cognitive load you have when reading a bit of software. So another question is coming up. So would like it if people would put in their answers. If we have this function, foo, which takes a mutable car, red car, we print out the car, we pass it to the paint method, and we print out the car again. Do these two print statements print out the same thing? The thing here is, we don't know. It really depends on what the paint method does. Does the paint method paint the car a different color? Yeah, then these two things will probably print out different things. If the paint method makes a picture of the car, or makes a painting of the car, then these two things will probably print out the same thing. The thing is, we don't know. The only way for us to know is if you take a look at the paint method and see what the body is. And then we just have to hope that at the end of the paint method, it doesn't call another function that passes the car. So now we also need to look at that function. So just in order to understand what these 3 lines of code do, we need to, if we're unlucky, take a huge part of the program, read that, all put it into our heads just to figure out how it works. And this is what I mean with high cognitive load. In order to understand this bit of the program, we need to understand a big other part of the program. We can't really apply local reasoning. So if instead we'll make an immutable car, for this we'll use Java 17's records, where a car has a color and a brand, and a record basically just is there to create an immutable value class, and it automatically generates getters for you and equals a hashtag. And if our method would be like this, where foo now passes an immutable car, and it asks the question, do these two things print out the same thing? The answer is, of course, yes. These things can only print out the same thing because the car is immutable. And this is, again, the advantage immutability gives, because instead of having to figure out what the paint method does, I can instantly tell how this bit of code works. So immutable objects give us the power of local reasoning. We don't need to know all of the code. We can only know a bit of the code. But of course, immutability also has downsides. So what if you want to change value? Well, currently in Java, the only way we can do that is by creating a new object and return that instead. So we'll create a new instance of immutable car, get the brand from the old car, and pass blue as a color. This is currently the only way to do this in Java. There are some other tricks you can do. You can also use Lombok's add builder and do a car.toBuilder and then only set one property. That's a thing you can do. Or you can wait a bit because they're working on a new Java feature, Withers, that works on records, where you can do exactly these kind of things in a very easy way. So Java is actually moving towards language features that support this paradigm a bit better. And the nice thing is, because we are now forced to return a new instance for any changes, we can now instantly see state changes within our code. So do these two print statements print out the same thing? Probably not. It could still be the case that it just returns its input. So we're not 100% sure, but at least we can instantly see there's a state change going on. I need to check blue car here again. It also has the advantage. Now I can also assign it to a different variable name. If previously everything was red car, suddenly I can add a new variable name to the car, indicating helping me with what state change could have occurred. So just by using immutability, you also force your code into working in a certain way, which is generally beneficial to local reasoning. But of course, everything in software engineering has a trade-off. And anyone who tells you this is the perfect solution for everything is either trying to sell you something, lying to you, or both. Because everything I'm saying, everything has trade-offs. You pick one thing in favor of something else, and you try to figure out which trade-offs you can deal with and which advantages you really need. So in our case, the trade-off is performance, because we are creating more objects than we would use with mutable state. With our asterisks, that's not always the case. Sometimes it's actually more performant to use immutable objects. For example, there's a reason why strings are mutable, because if something is immutable, you can point to it with as many pointers as you like, and therefore, because it's immutable, so it can't be changed, so it's a safe thing to do, which means that if you have the same object many times, instead of having that, you can all points to one object, which actually saves some memory. And again, this is why strings are mutable in Java. So if you have the string A, you don't have to have two instances of that object. You can just reuse the old one. So, but in most cases, you are creating more objects. So is this a bad thing? Well, it really depends, of course. If, in my experience, any normal enterprise application won't actually notice this. I don't know if anyone here does things like Advent of Code. Advent of Code is like a yearly programming competition. It's free to participate. It's in December. It's very fun if you haven't done that yet. But yeah, there you start doing things where lists contain millions of elements. Yeah, or even billions of elements. On those kind of things, yeah, you will definitely notice the difference. But on most enterprise applications I worked on, I didn't really notice it. So then the trade-off becomes, do I have nice low cognitive load code versus very performant code? And since performance is basically neglectable, the difference, I tend to go towards immutability and have well, easier to maintain code. If you are still have a problem where, oh, this problem is really difficult to solve with immutability, I want to add some mutable state, there's actually a trick we can use. So if we make sure our function has an immutable input, strings are immutable, and an immutable output, and all the mutable variables, in this case our builder and our variable, stay within function scope, it's not actually that bad, because the rest of the application can still reason in immutability. An immutable string comes in, an immutable string comes out. And since none of the mutable things are escaping the function scope, it's fully thread safe and it's just safe to use. I could replace this implementation with a recursive algorithm and then change it back again, and the rest of the application wouldn't know. So if you use mutable state, please try to keep everything function scoped. And in that case, the rest of the application doesn't know it, which means the rest of the application isn't affected by it. This is also where some function programs can be a bit dogmatic. We're saying that no mutable state is allowed. But if we just look at what problem do we try to solve, this still solves exactly the same problem. So just you're free to use mutable state, just try to keep it function scoped as much as possible. Another thing, talking about state, is the thought of making legal states unrepresentable. So something should only be created in the correct state, and it should be illegal to change it to an illegal state. Basically, make sure that content of all the objects is correct at all possible times. This is a whole separate subject, but I just want to talk about a bit of pet peeve of mine, nullable fields, because I had to solve way too many null pointer exceptions. So I tried to program in a bit different way to figure out how I can prevent these null pointer exceptions. And it turns out not using null is actually quite a good way to do that. So let's talk about nullable fields. Some fields are really optional fields. For example, we have a person here, we have a first name, a middle name, and a last name. I have a middle name, Vande, but a lot of people don't have that. So this is a truly optional field. So this being nullable is sort of okay by me. Although you could also use an optional, but this works because it's an optional field. If you would, however, look at our contract, which has a text and a nullable signature, is that really a nullable field there? Because the signature is probably null when the contract is created, but at some point it gets signed and then it gets a value. But because it's nullable, it does mean you have to do signature type checks all over the code. Like if you start a project, we need to check if the signature is null or not before we start doing the project, and otherwise we have to go into a whole exception flow. But again, should that be a nullable field? Or are we actually hiding a state change here? Because what we could also do is instead create a contract which only contains the text, and a second object, a signed contract, which contains a text and a signature. And at the moment a contract is being signed, you start creating a signed contract. And this makes sure that if you start a project, you can ask for a signed contract instead. And now you don't have to do any checking whatsoever. All these checks are now replaced to the factory that creates a signed contract. And this is a very powerful way if you model state changes as objects, then you can do these two tricks. And it's also exactly the same way of thinking as you saw with composition. We start thinking in state changes. We have some JSON and we turn it into some parsed input. And now we have a parsed input as an object to represent the state change. Of course, there's also some problems with this in some code bases. That this trick won't work on every project. But I do wanted to tell you about the way of thinking. And maybe if you have a lot of problems with nullable fields, this is an angle you can consider in attacking that problem. So the key takeaways here is that state is difficult. Mutability is by definition more complex than immutable state, because mutable state has the complexity of time added to it. It's not inherently bad. Sometimes you just need mutable state purely for performance stuff, but at least try to keep it function scope. And we can use a type system to remove nullable values. A question outside the scope: how are parallel streams working in Streams API? Since indeed it's a bit out of scope, we can talk a bit after the talk, I think, if that's okay with you. And then I'll continue on error handling. So things will fail in code. Connections can drop, you can get overflows. Errors are just part of programming. A good way to reason about errors, I noticed, is dividing them into two separate categories. And that's recoverable errors and unrecoverable errors. So recoverable errors basically mean if the error can be recovered in any way by any of the callers. So a way to recover an error could be using a default value. It could also be by using an alternative code path. For example, if your database is down, maybe you have a cache that you can get values out of. Or just recover by sending back a different status code. For example, if your user input isn't correct, then you can recover from it by returning a 400 status code saying, oh, your input isn't correct. And everything else are technical errors. Those are the unrecoverable things. Basically, stuff that returns a 500. For example, if your database is down and you don't have any backup, yeah, what are you going to do? You'll probably retry a few times, but you can't do anything with the data because there is no data. So you might as well crash. So on one side, recoverable errors, and the other side, unrecoverable errors. And there are a few strategies that people use to deal with these kind of errors. The first being hope. This is a very, very popular strategy, and we'll just hope things don't go wrong. And other two very popular things are runtime exceptions and returning null. So let's take a look at those. Here we have our divide function that takes two doubles and returns a double. If the second operand is 0, then, well, we can't do a division by 0. So instead, we'll save by throwing a runtime exception. And otherwise, we return the correct result. The thing about this, however, is that the function signature is lying to us. Because the function signature says, given two doubles, I return a double. While the actual behavior is, given two doubles, I either return a double or I kill your current thread. Because that's what the runtime exception does. It kills the current thread, which is quite extreme if you ask me, for this function to decide. And the only reason I know about this behavior is because I took the time to write some Java up that it actually throws an exception. And of course, you all write Javadoc on top of your functions, or at least read all the Javadoc above your functions that you're calling. And if that doesn't happen, I hope you have some very good test coverage. Otherwise, you can get a nasty surprise in production. So this is a problem with runtime exceptions. You can't really see them without actually having to look at the code or the comments. But they do have a big impact on your code. They crash your current thread. So does this mean you shouldn't use runtime exceptions? Well, that depends. Crashing the current thread doesn't have to be a bad thing if the error is unrecoverable. If you're at a point where no matter the context that's calling me, nothing can recover from this, then runtime exceptions are actually exactly what you want. Just kill it now, we can't recover anyway. So for unrecoverable errors, runtime exceptions are actually quite good. Another thing that's quite popular in Java, and that's something that I think we should stop doing in general, is returning null. So null has exactly the same problems as the runtime exception has, in the terms that the function signature lies to us. Well, in this particular case, you might figure it out because it's capital D double. But if it would return a person instead, we wouldn't have that information. But in base, it says given to doubles, either return a double, or sometimes you'll get a null pointer exception. So the problem I have with returning null is that the function calling this function, what is it going to do? It will have to do null check. But what does it do when this function returns null? Well, in practice, I've seen a lot of functions then just return null themselves, which means the function calling that function now needs to do a null check. And what does it do if it's null? It probably returns null itself. So now the function calling that function needs to do a null check. Basically, one function on the very bottom starts returning null. It tends to chain up all the way and infecting your entire code with null checks. So that's why I don't really like returning null. So are there any alternatives? Well, there's checks exceptions, as someone mentioned in the chat, optionals, and there's seal types. So anyone here likes checks exceptions or hates checks exceptions? Because a lot of people seem to have a strong opinion about these. Most people tend to hate checked exceptions. But if you think about it, checked exceptions are actually quite interesting. Because what do checked exceptions give us? Quite a lot of things. First of all, it shows our method can fail. Because now we can actually see in the function signature, this function either returns a string or it throws a found exception. So I instantly know this function can fail. And in that sense, it also shows the function has multiple return types. It has a correct path and an error flow. It also forces a higher context to recover. And the higher context, the caller of this function, can either decide to recover from it or just fail itself. But now it's a choice of the calling function instead of this function. So the one context might be able to recover from it, another context might throw a runtime exception anyway. But at least this function is no longer deciding if the current thread should be crashed or not. It also forces the caller to reason about error. You have to do some checking. You can't just use hope as a strategy anymore. They're also fully type checked because you have to catch a found not found exception. So you have type checking in there. And this kind of makes them great for recoverable errors. If it can be recovered in any way, checked exceptions are actually quite good. So why do people hate checked exceptions if the idea behind it is actually quite interesting? Well, that's mostly because the implementation is quite bad, in my opinion. First of all, you need to have this whole try-catch block around it, which, well, is ugly. And since try isn't an expression in Java, you have to work with statements again and such, and it leads to messy code. But not only that, let's take a look at what kind of checks exception we tend to see. Things like found not found exception. If you look at cases, what are likely cases that won't be recoverable for many types of applications, Well, a lot of applications that try to read a file are kind of dependent on that file being there or not. So um, turning all those things into checked exceptions, well, that just means in practice, in most cases, they get ignored because, yeah, if this fails, it fails anyway. So the API isn't that great, and the exceptions that they picked, yeah, those tend to be unrecoverable things, which leads to annoyance with software engineers. I think the problem with check exceptions, they might be try catch, then thrown using unchecked exception. Could be. So instead of check exceptions, since Java 8, we now have an optional. And this has basically the same ideas as a checked exception, except that the API is much better. So now our function signature still says, given two doubles, I either return a double, something contain, I always return an optional that might contain a double. So our function signature is now very honest. And the API of the optional is also way better. It has built-in methods to recover with or else get, or even or else throw if you just want to crash the current thread. It's composable with map and flat map. But the downside of an optional is it doesn't really contain error information. So we know things went wrong, we just don't know why. So if data get person from a database function returns an empty optional, we don't really know why, as in, was it because there was no person, or was it because the database connection failed? So for that, we can actually use a trick since Java 21. We can model errors as types, basically just like signed contract. Because if you think about it, a function type is basically either a success or a failure. So a function always returns a success or a failure. And we can create an interface for that called result, which is either a success or a failure. Success containing the result, and failure containing a string with error. And we'll make it a sealed interface, which is something we can do since Java 19. And this makes sure that the compiler knows these are the only two possible implementations of this interface. And that's going to be very handy. So we'll rewrite our divide function to now return a result, which is either an instance of failure or an instance of success. And now we can use Java 21's newest feature, pattern match switch statements with instance of checking. So we can now switch over the results of a result, which is either an instance of success, and we have access to value like this, or an instance of failure, and we have access to the error like this. And we don't need a default here, because we used a sealed class. The compiler knows these are the only two possible implementations of this interface. So if we would ever add one in the future, this switch statement will no longer compile. So this is fully compile time safe. And this is a whole different way to reason about errors. And we call a function. If it's a success, we go this way. If it's a failure, we go that way. So I've seen some people chat. Let me first talk about the key takeaways. Think about your error paths. Model them if they're recoverable, as in runtime exceptions are not the only option. Things like optionals or even creating your own sealed types. Those are also good ways to help with fixing recoverable errors. So let's see what the chat says. Can we use annotation for declarative error handling? Yeah, that's a Spring handles most of the exceptions, and that's an easy way to handle it. That's true. The downside, however, of that approach is if you have a lot of recoverable errors, so things that need to return a 400, for example, you can do this with Spring exception handling. The problem starts when a lot of components all start creating their own errors and you have to create tons and tons of error handlers and just hope that you manage to catch all of those. So by using a more optional or sealed type approach, like I just mentioned, then at least you have in your controller, it's more fully type checked, as in you're forced to deal with that error and you can't forget about it. Doesn't mean that you should indeed stop using that other error flow, but that's the downside of it. You have to, there is no compile time check that you manage to get all the errors. And what we're trying to do here is bring error handling from runtime to compile time. So nothing wrong with the approach, but this is the trade-off. It's instead of a compile time solution, it's now a runtime thing you have to check. Now, sealed class is in Java 15. Okay, sorry, then I should change that slide. But since Java 21, when with the whole sealed class and pattern matching, that's when we get the real power of sealed classes. They're actually an amazing feature. And we're really looking forward to what we're going to do with that. I actually have a different talk about that. But since we have 15 minutes left, let's continue with the last topic, side effect management. So in software engineering, we have something called pure functions. And this is an attribute a function can have. And it can have this attribute if it has these three properties. It's idempotent, it's total, and it's referentially transparent. So what do these things mean? Idempotency just means that it's repeatable. Calling it with the same arguments always gives back the same result. Like the plus function is repeatable, giving the same arguments, it will always give back the same result. Our divide, and this is also okay if the result is an error, as long as it's consistent and it's always the same error. Total basically means for every input, it should have a valid output, which means an error isn't okay anymore because that's not a valid output. So a plus function is total. For every input, it has an output. But the divide function we wrote, that one is not total because when the second operand is 0, it throws an exception. So our divide is not a total function. There is a trick we can use. If we make the divide function return an optional instead, now it becomes a total function because now it always returns an optional. It might have a value or not, but it always returns an optional. And that's how you make a non-total or partial function and turn it into a total function. And referentially transparent. This basically means the function has cannot alter state outside of the function and cannot use state from outside the function. A good way to think about it is the whole function body should be able to be deleted and be replaced by a lookup table. So a plus function could be replaced. The entire body should be able to be replaced by a huge lookup table that basically if the first operand is 1, the second is 1, then the answer is 2. The first operand is 1, the second operand is 4, the answer will be 5. Not a good implementation, but this is more about it. It can be called referentially transparent if it could be replaced by that. And in practice, like I said, that means it cannot alter state outside the function and it cannot use state from outside the function, or at least not mutable state from outside of the function. And once a function is pure, that's a great thing because pure functions are very reliable, they're extremely consistent, and they're very easy to test. We don't need mocks for those. So what are side effects? Side effects are everything that makes a function not pure. Some very good examples of that are any form of I/O, like reading or writing to files, calling a web service, calling a database operation, the combination of getters and setters, because setters change things from outside the scope, and getters will now access a mutable variable from outside the scope. Just getters with immutable variable is fine. That's a referentially transparent. But also things like logging. Logging also changes state outside the function in terms of it adds something to console, adds something to a file. If the file would be full, the application would crash. Although a lot of function programmers also think it's okay to use logging. That's not generally considered a side effect, but officially it is a side effect. And yeah, side effects are nasty. These are the ones that cause our code to be unreliable. And these are the ones that cause our code to be very difficult to test. We do need them, however, because you literally can't build an application without side effects that actually does anything. So we need these side effects, but they cause problems. Question. So basically, all the mutable states or values or entities are side effects. Yeah, a mutable state is generally a side effect, since, well, it depends on if it's within function scope, it's okay. But anything outside of function scope, yeah, that's a side effect, because now calling that function changes a value outside of it, which might cause a different part of the program to behave in a different way. For example, the setter makes so that if someone else calls the getter at a different point in time, the getter will have a different behavior. So yeah, in that sense, mutable state is side effect. If it's within function scope, it's okay, since you're very in control of that. But to give an example of that side effects make code hard to test, if we have this function that calculates all the seconds between now and a date we pass, the first thing to do is we get the current time. Then we calculate the amount of seconds between now and the date we passed, and we return that. And now for you, the question is, how would we test this code? This is usually the point where there's someone in the room who knows that, oh, there are actually ways to test this, because they, in Java, they actually did a lot of thinking in how to design basically the third iteration of the datetime library. So there are ways to test this, but there's a problem here. And why is this hard to test? Well, it's because we get the current time here. So the reason this is difficult to test is because this function actually has a hidden input, namely now. Time is a hidden input into this function. And because that input is hidden, it's very, very difficult to test. And this is a good way to think about side effects like this. So the way to solve this is, instead of making it a hidden input, make it an explicit input. If we would pass the now as a parameter, suddenly this function is very easy to test. It's not even a pure function. So by making side effects explicit instead of implicit, so we have very testable code. The same goes when you try to read a file. If you try to read a file, the reason why it can sometimes fail and sometimes succeed is because the file system is the hidden input into that function. If that function would be given this file system and this file, it would be a pure function. It would be completely consistent. But because we don't tend to pass a file system as an input, it means it's a hidden input, and this is what's causing all the problems. So most side effects are difficult to test and cause problems because they're hidden inputs, and therefore you can't control them. Another example of this is how to test this function. Well, how do we recognize a hidden input in general? Not this simple example. Well, any form of side effects tend to be hidden inputs. And one good way to figure that out is actually by writing tests. If a function is very difficult to test, you'll instantly see, oh, that's probably because of a side effect. And at some point, if you start practicing a bit in recognizing side effects and start thinking into side effects and pure functions, this stuff will become very easy. And you can suddenly explain a lot of things. This is a good example of that, actually. So we have a function that gets a user from a database, does some arbitrary business logic, and stores the user in the database again. So how would we test this function? Well, these days, there are some good ways to do it. One thing we could do is use an in-memory database. We could or we could mock it. We could use an in-memory database, or we could use something like test containers. But the problem with all those approaches is that we do need to have to set up the whole database, make sure it has the correct contents, then check all the things, make sure it works if all the tests are test after test, also make sure it works if tests are run in a different order. So it's all doable, but it's not ideal. And all that to test a bit of logic. So a good way to solve this problem is very simple. if we separate the logic from the side effect. So if we now want to test our business logic, we can just pass it any user. It doesn't care where the user comes from. And in the end, it returns a user and it doesn't care what happens to the user. So if we want to test our business logic and we separate them from the side effects, namely the database things, suddenly this function is extremely testable. It is very easy to test this. It's still very difficult to test foo because, again, our application needs side effects. We can't build an application without side effects. And there is a point where we would still need to test for those. But at least we have the option now to separate a bit of our application in a separate way, in separate unit tests that don't need to do any buildups. So any complex test of algorithms and such can now be performed without having to do whole database, build up your whole database and all that kind of thing. So separating business logic from side effects is actually very beneficial because now you create a pure domain layer. That's very reliable. And I call this the orchestrator pattern, where an orchestrator has the job of first calling the side effect, do all the error handling, then pass the object, if everything's correct, pass the object to the logic layer, and then pass that return type to to a different side effect, for example, store it in the database again, and do error handling again. And now all components are basically the most simple they could be. It either does a side effect, it does orchestration, or it does business logic, and nothing else. And if we start doing this more and more, like I said, we start creating a pure domain layer. Like all our business logic will be pure functions, which are extremely reliable and very, very testable. And around it comes an anti-corruption layer, which handles all the side effects and does orchestration and such. And if we would draw this as an image, it would look something like this with our pure domain code. Around it, there's an anti-corruption layer. And around those are the side effects like databases, web service, front end, or email service. So does anyone recognize this picture? This is basically hexagonal architecture, or pipes and adapters, or onion architecture. Basically, the whole reason that thing, a clean architecture, basically the whole reason, or one of the main principles behind this, is just side effect management. If you separate business logic from side effects, you automatically sort of get something in this direction. And on one side, I think it's a bit weird that we know about side effect management for years and years and years now, and suddenly we need a new word and it becomes hip again. On the other hand, I'm very happy people do side effect management now. But this does show the power of knowing the fundamentals. If you know about side effects, if you know about what problems they cause, and know about how to separate those from your business logic, if you understand that bit of fundamental knowledge, now something new comes along, like a hexagonal architecture, and you can instantly understand how that works, just because you know this bit of fundamental knowledge. So all these things I talked about today, I use on a day-to-day basis as a job as software quality experts to look at other people's code to figure out what improvements could be made. And even though I never saw that code or even that language before, this fundamental knowledge allows me to reason about things that I haven't seen before. Because in the end, most of the things come back to these fundamentals. So even though most people know like what immutability, side effects, and error management is, but really understanding them and really focusing on what it actually means, yeah, that does help you a lot in understanding newer stuff. So the key takeaways here, you need side effects. You can't build an application without them, but do try to identify them. Every time you look for your code, try to figure out what are the side effects and what's pure code. And try to make the side effects explicit. Basically, separate them from your business logic. And this will automatically move them to your edges. And this is how you create a clean architecture, just by doing side effect management. And that kind of concludes our talk. where today we learned that composition can help with problem solving. Every problem can be broken down into smaller problems, and solving those solves our bigger problem. And consider using streaming API to practice that. Be very careful with state. Consider immutability. Nothing wrong with mutable state. Just try to keep it function scope. Don't trust the happy path. Hope isn't a great strategy. And consider other options except runtime exceptions, especially for recoverable errors. Be aware of your side effects and choose where they take place. But most importantly, be pragmatic, not dogmatic. You don't need to do all this stuff in every application out there. Just be aware of it and make a conscious decision. And if you think I'm already doing these kind of things, well, then it turns out you may already be more of a functional programmer than you thought you were. And with that, it's the end of my talk. If you have any questions whatsoever, you can ask them now. You can send a message on Twitter. I'm more active on LinkedIn and such. You can find all those contact details on my website, tsvendeven.nl. And if you just want to see it, you can find them here. So if you have any more questions, feel free to post them in chat. Then I can see if I can answer those. And if not, I would like to thank you all for your attention.
Yep. Thank you so much, Tees, for this amazing session. Really, you nailed it. And really, we learned new things really in this amazing session. I think there is a question. Is it possible today to, yes.
Yeah, if it's possible to create an application that follows a pure functional paradigm. There are actually loads of applications that do that. So the answer is definite yes. If like I never programmed in Haskell, but that's basically famous for it, where you can write something in there, and if you manage to get it to compile, it will probably just work. Getting it to compile is the difficult part because it checks everything and you need to prove everything to the compiler. But once you get it to compile, the compiler really helps you a lot. So yeah, it's definitely possible to create a fully functional application. Can you drop this GitHub? Yeah, sure. And for full completeness, I'll also do that.
I think
for some reason I can't post these in the comment. Maybe it doesn't allow links because I assume that's to prevent spam. So, but on my website there's also an easy link on that. So that would be the easiest way to do that.
Yeah, no.
Regarding parallel streams API function question. Let's see what that was again. How are parallel streams working in the streaming API? Basically, it tries to perform all the operations parallel. This is where it really helps if you operate on immutable objects. Put some dots in between, yeah. This works really well if all the operations are pure functions, because pure functions have the advantage, like they're referring to transparent, they don't change state outside of the function scope, which means they're safe to run in parallel. If you have a map operation that mutates or uses mutates a variable outside of the stream, then it's very dangerous to do it in a parallel way. But if all your functions are pure functions, parallel streams basically know it's safe to run all those operations on different threads. So it can, for example, divide your list into 2 different lists, run all the functions on both of the lists, and then combine the result again. So that's how parallel streams sort of work. Most of the stuff you don't need to deal with. Java does all that, but it's important that the functions you supply to that are all pure functions. And again, of an example of how knowing what a pure function is and how it affects things can help you understand those kind of things. How do FP concurrency models contrast with traditional concurrency approaches in Java? Not that different, but in the sense that exactly what I said, they're very conscious about state and just prevent problems from occurring. If you don't use mutable state, then concurrency is quite easy, actually. But parallel work depends on the nature of the task. Yeah, and the thing is, if you do that parallel in a stream in Java, it doesn't actually mean it splits it up into different streams, or does it in any parallel way. Because if you would try to if you have listed two elements and try to do it parallel, it's actually cost way more resources to split up the thing and merge it together than to just do those two elements. So if you say dot parallel at the stream in Java, it's only a hint to the compiler saying that, oh, this is safe to run parallel, and then when you run it, it will try to either do parallel or not. It's not your decision. It's only a hint to say it's safe to do parallel. So regarding performance, it depends. If you have a huge list, yeah, definitely. Then it will help. If it's like under 100 elements, I wouldn't bother doing parallel operations. Also, things will get a bit better with virtual threads in that regard. Let's see. Does that answer all your questions so far? Does TDD help with move side effects? Well, not per se in the sense that TDD itself doesn't do that, but it can help you in this, when you're writing tests, when you figure out, oh, it's difficult to test this bit. Why is it difficult? Oh yeah, because this function does a database call. Hey, what if I just turn whatever comes out of the database and make it an input? Now suddenly it's very easy to test this function. So in that sense, TDD can help you identify side effects, because side effects will make it very difficult to test your function. So in that sense, it can help. So basically, it means that might or not can be executed parallel. So in Java, we don't have the opportunity to explicitly say that there should be executed. There are, but not through the streaming API. Like if you just use the streaming API, the parallel is a hint to the compiler that it can be run parallel, but that bit gets decided by Java. But you can do your own, or you can, nothing stops you for doing things in parallel, especially now we have virtual threads. But then you have to do things yourself. Oh, and I think in Java 23, there comes a .parallel map operator in the stream API, but I'm not 100% sure if that's guaranteed to be parallel. I haven't looked into that. As far as my knowledge, you can't specifically say it needs to be run parallel. But yeah, maybe in Java 23 with the new options, but not sure. I haven't looked into that bit. Yeah, and thank you all for your attention. I hope you learned something out from it. And if you have any feedback, feel free to send me a message or any more questions. Most of the stuff I talked about, I learned because I was coaching and teaching people. So anyone with any questions also helps me with my next talk.
Yeah, thank you so much, Tees. I think with that being said, I think there are not more any questions anymore, please, guys, if you have. Yeah, I think
Yeah, you can
we're
always
wrapping.
send me anything,
Yeah,
message on LinkedIn, also in the future.
yeah,
I like to
sure,
talk
sure.
about this stuff.
Yeah. Yeah, so thank you everybody for your great participation and for your questions and for your attendance as well. And all the thanks to Mr. Tees. Thank you for this insights and amazing session. And looking forward really to hosting you again and again in our judge. Thank you so much.
Yeah, well, thank you for having me, and see you next time.
Cheers. Bye bye.
Goodbye.